Welcome, class. So I gave you this question on the workshop here where you have to basically tell me what the mass of a substance is based on the data acquired from a mass spectrometer. So I think a few of you have said you're a little confused about what exactly is going on, so I thought I'd give you some pointers. Mass spectrometers are super cool. I've actually used one some in when I was in college to do some research. But basically what it is you have a setup where you have basically some, I don't know, source, some way of achieving an ion. Okay, so an ion again is a charged particle. So we have some charged particle like a atom that has a net, let's say, positive charge of positive Q. Okay, so we have some ion of some atom that has a charge of just positive Q, and it is basically passed through a region where a voltage difference exists. So you have some voltage difference here, okay? And so as a result of that voltage difference, you will cause your charge to accelerate. So really voltage difference, right, means that there's like an electric field. So we have some sort of E field here. And that electric field is going to cause our charge to accelerate because there's some change in voltage. Sorry, I think my dog sees an animal in the backyard and he's losing it. 1 second. All right, well, I let Gus outside, so maybe we'll hear a little less of his whining. But anyway, so yes, you have an electric field region caused by a potential difference that will cause your charge that's generated to accelerate, right? So let's go ahead and, so here's our charge. It's going to accelerate through this region, and then eventually, once it's done accelerating, it's going to enter into a region with a uniform magnetic field. So let's go ahead and, let's say, okay, our potential difference leads us to some area where in that area we have a uniform magnetic field. Oh, okay, that was into this picture. So let's say that we have a uniform magnetic field coming out of the page, something like this. My art isn't amazing, but you get the idea. So we have a uniform magnetic field coming out of the page. And if we do the right-hand rule of V cross B, once our charge enters into this field, what's going to happen? Well, it's going to experience a net force, right? And that net force, when it first enters, is going to be down, and that will curve it, and so then it will be going through kind of a uniform circular motion type path where it travels a net distance that we're told in the problem statement of x. So this here is our distance of x, and so if you think about really this kind of path of uniform circular motion of radius r, you can quickly observe that x is just going to be equal to 2 times r. So if we think about our charge when it's, let's say, right first entering, right, keep in mind when our charge is here, the force will be down. When the charge is, let's say, over here, the force will be this direction, right? Because its force is perpendicular to the velocity vector and the B field, because, again, force exerted on a moving charge by a B field is QV cross B, right? And so in this case, we're basically being told that we have a situation where our velocity vector and our B field are perpendicular to one another, and then our force will then be perpendicular to that. So we can conclude that the magnitude of our force being exerted is just going to be equal to Q times the magnitude of V times the magnitude of B. And so we're first asked to determine what the radius of its path is going to be, right? And so I tell you that we have this radius over here, R, right, of its curved path that it goes through. And so we're asked to figure out that radius in terms of the B field, the charge, and some other things. So if we think about it while it's going through that curved path, if we were to do some of the forces, right, equals MA, well, the only force is the force due to the B field, right? And that's going to be equal to M, and it's going through uniform circular motion because it has a force causing it to go through a circular path perpendicular to its direction of velocity, and so its acceleration would just be the centripetal acceleration of V squared over R. And so we know the force is QVB, and so that would be equal to MV squared over R. You could easily solve for R. And then for part B, you're asked then to figure out, okay, given that information, we need to first then figure out what its speed is going to be. What is that V value going to be as it enters in, right? And so for that, you need to think about how it will be accelerated with this change in voltage, okay? So think about the fact that you have some potential difference, and we know that change in potential energy, right, is Q times V final minus V initial, right? That's your change in potential energy, and we're also going to have a change in kinetic energy of our object, which will equal 1/2 mv squared. And so change in potential energy gives you your change in kinetic energy, so you should be able to solve for the velocity as well. And then from there, I think you guys should be able to figure out the rest as you just do a bit more algebra, really, to put these things together and figure out what this element is, okay? So go ahead and start from here. If you have more questions, let me know, but I hope that helped clarify what a mass spectrometer is and how it works. It really, again, uses a potential difference, accelerates a charge, usually an ion, positively charged atom, and moves it through a uniform B field, and you can measure where exactly it hits, what distance away from where it started it hits, and you can then use that in combination with the magnitude of your voltage in your B field to determine exactly what element it is. So it's a great way to determine what a substance is made up of if you can generate ions of that substance and shoot it through here. So anyway, give that a go. Let me know if you have any questions.